the theorem is U3, or as it's come to be known, advanced counting for dummies. So what one wants to know is how to rigorously define degrees of freedom in a quantum field theory, which is kind of a non-trivial statement. For instance, if you take some bland generic quantum field theory and you place some hard cutoff, you're cutting off a certain number of modes of each canonically quantized field you're putting into this field theory. And so there's not some rigorous notion in which you can say, I have this degree of freedom and this degree of freedom because you've chopped up your space in some sense. But in conformal field theories, one can make this notion very precise. And so I'll talk about two approaches that I've been, one failed approach and one in progress approach about how to count degrees of freedom and show that they decrease along renormalization group flows in 3 dimensions. And so the kind of canonical statement is what's called the A theorem. It's called the C theorem in 2 dimensions. And it says that the number of degrees of freedom is counted by some parameter that I'll talk about soon in a UV theory is strictly greater than the quantity defined in the IR. And so you can kind of intuitively think of this in, if you look at Wilsonian effective actions, one defines a quantum field theory by some effective action with a cutoff lambda. And when you integrate out modes that are above this cutoff lambda, let's say, for instance, you're working with QED with an electron or a muon. When I go beneath the muon mass, I'll get effective operators that don't contribute these muon modes, but their effects will be felt in terms of renormalization of local operators. But I'll have, in some sense, less degrees of freedom. But the only way in which this is made precise is by going to conformal field theories. So there are kind of 3 canonical ways that the A theorem has been established. One of them simply doesn't work in 3 dimensions. Another, Marcus and I tried, it doesn't work in 3 dimensions, so we're really hoping the third one shakes out in 3 dimensions. But for reasons of symmetry, 3 ways to prove something, 3 tries, it should work.
So when we're talking about D equal 3, these are spatial dimensions?
Yeah. Yeah, so this is in 2 + 1 dimensions.
Oh, okay.
Yeah, no, it's this statement has been proven in 2 and 4 dimensions, and most of the way in 6.
I see. So it is known in 4 dimensions.
Yeah. This is work I'll discuss shortly as well. So there was a proof in '86 as Zamolodchikov about how these renormalization group flows work in 2 dimensions. And in 2010, maybe I should have made these bubbles slightly larger. Komargodski and Schwimmer, using spurion analysis, showed or proved the A theorem or the C theorem, depending on which dimension you're working in. That this notion can be rigorously proven in 2 and 4 dimensions. And there's been a lot of recent work on entanglement entropy, which has its modest beginnings in black hole physics, that has been shown to have some connection with the ability to count degrees of freedom in quantum field theories. So the first approach, which sadly, because the conformal group is infinite in 2 dimensions and can't be used elsewhere, is that of Zamolodchikov, but it's fairly intuitive. So Zamolodchikov says that I define a quantity C. This curve is, of course, how one represents all renormalization group flows. It was in a paper Marcus wrote, and whenever I am trying to think about something that represents a renormalization group flow, I just wind up drawing this line for some reason. So one believed idea is that the asymptotics of quantum field theory, in the sense that when you take the theory to 0 cutoff, when you take the theory to infinite cutoff, it's a conformal field theory. So in 2 dimensions, it was shown that if you have a theory that's conformal in the UV, and then is conformal in the IR, then CUV is greater than CIR. And this C is related to the trace anomaly in 2 dimensions in the following way. And this is because T is not a primary field, so it has some non-trivial transformations. And so, in 2 dimensions, as kind of a keystone example that you should keep in mind, I can make this very precise in the sense that I write down the action of a free scalar field, and I can exactly compute what this contributes to the trace anomaly. And it contributes just 1. So this is a conformal field theory. It's massless. So what I can do is perturb this with a relevant operator, for instance, boson mass term, and I can integrate down beneath the scale m, and then I flow to an empty theory, and then CUV, or CUV in the sense where the boson is massive, or is massless rather, has some well-defined central charge. I add some mass term, or some dynamics to generate this mass term, and I flow down, and the boson is integrated out of the theory, and so I have no degrees of freedom. There's some subtleties associated with what the dilettante contributes, but I wouldn't worry about that yet.
So my mind was elsewhere when you wrote this equation. R is just the usual general relativity.
Yeah.
R. Okay.
So as I said, Zemlogicon proved this, but the actual proof that goes into making rigorous this notion is a bit involved and requires the use of properties of the conformal group in 2 dimensions that don't carry over to other ones. So in terms of approaches that one has for d equals 3, this is out the window.
So let's see, the one thing you did give in your introduction was, why do I care?
Wait. Oh, you said the one thing. Well, my kind of snarky answer is the maxim of, Greta Garbo, Audrey Hepburn had this maxim of you can never be too thin, too rich, or know enough quantum field theory. So if one lives by this, one doesn't need to motivate these talks. But
I mean,
the actual
in other words, are there any phenomenological consequences at some level somewhere?
Not directly. So you're more interested in the asymptotics of quantum field theories. So Marcus and others use the work of Komargodski and Schwimmer to show that if the A theorem or some analog of it is true, then this rules out certain renormalization group flows, things like chaotic renormalization group flows or limit cycles that you'd get in classical systems like the 3-body problem. And so it shows that in some, it also rules out the possibility of scale invariant field theory not being conformally invariant. This is work that Cara, Marcus, and Valentina have put some paper. This is kind of the money result, is showing that there's no difference between these objects. So our next approach is what Marcus and I tried and finished as of October, November. This is unpublished because you don't publish garbage. It's wrong. So you guys aren't enjoying my jokes. It's nearly okay. So in 2010, Komargodski and Schwimmer proved the A theorem and the C theorem in 2 dimensions. We'll just call it the A theorem for brevity, because God knows there are enough letters for what these objects are called in various dimensions. And so what they've done is they use spurion analysis. So in even dimensions, they wrote down every term that could contribute to the anomalous action. This is in 2. And what you do is you work in a frame in which you maintain conformal invariance. You redefine G to be equal to tau, your original G, where tau is now the dilaton. And you look at the properties of scattering amplitudes of the dilaton, and using things like unitarity, you can say that the coefficient of this action under our G-flows has to have some sign. And so this one is kind of trivial because the only thing you can write down is R, and this will generate some Wess-Amino term that you can use to show that this action has to have some positivity property. There are things about anomaly matching, but I didn't think that people really care about how to make sausage in the middle of this. In 4 dimensions, it's a bit more complicated because you can write down 3 independent terms, Ricci squared, Ricci scalar squared, Ricci squared, and Riemann squared. And so you have to slice these objects. I really should have put this chart out of the way for the rest of the time. So you have to classify these objects into Weil invariant pieces and non-Weil invariant pieces. And you have to make them consistent in the normal sense that you make anomalous actions consistent, which is that under a transformation, in this case a local scale transformation, this is the notion of consistency. So out of these operators, I can make Weil tensor that has some coefficient, which is sadly named C, and the Euler density. There's also it's a box R term, but that's a surface term, so it's not really relevant. So these are the 2 terms that I can write down in my anomalous action. And what Komargodski and Schwimmer proved is that this coefficient A is monotonic under our G-flows. And in some sense, in any even dimension, the Euler density carries the information about degrees of freedom under these RG flows.
Sorry, could you say again what's E4?
Oh, E4 is the Euler density in 4 dimensions. It's some linear combination of R squared, R mu squared.
There are 3 of them. Now you only have 2 of them here. Are they because they are not independent or something?
I don't know. So there's one that you can't make consistent. So there's one combination of these that goes as R squared that you can remove by a local counter term of box R. So you can do some scale variation to the operator box R and remove this anomalous term, whereas these 2 terms can't be removed by any local counter term. So the basic idea here is you take a gravitational action, you write down all the operators that you can that have the correct dimension and have the right Weil weight so that you get some non-trivial Wess-Amino terms. And then you try to use properties of the dilaton amplitudes to establish unitarity of the RG flows. So we did exactly that.
Are the signs up here in this equation included?
No, it's just to have it writing.
So why didn't they do D equals 3? It's because it's more difficult to write down all this.
Well, so there's some non-trivial folklore about there are no anomalies in odd dimensions. That's because people don't understand that you're not just looking for log divergences, you're looking for non-decoupling of the regulators. But even more importantly, there's no action that you can write down out of real gravitational degrees of freedom that has dimension 3 and Weil weight 3, unless you make the one assumption that we tried to make, which proves that not to be useful. And so that's what I'm going to talk about right now. So we attempted, using this Komargodski and Schwimmer method, to write down Wess-Amino action for gravity in 3 dimensions. The problem is that there's no way to do it using just R, mu, and Riemann. And so if you relax one condition, and you say that your metric can have torsion, now you have a dimension 1 operator of vial weight 1. So this is the torsion tensor. It's completely vial invariant, which is exactly the thing that will come to bite us in the ass at the end of this argument. And so now I can construct objects out of these torsion tensors, which have the right dimensions, have the right vial weight, but because of the ability to read will prove troublesome. So in the same way that you would take the curvature and its contractions and construct a gravitational effective action, you can also consider all linear combinations of things like del C, RC, C cubed, etc. And one can try to construct this gravitational effective action for torsion degrees of freedom. And so what one ultimately finds is that you can construct a consistent Wessmino action of the torsion, and it is so there are two terms, both of which are vial invariant, so they should give you anomalous contributions, and you should be able to say something about unitarity. Problem is that objects like C don't have gauge transformations under vial rescaling, so you can immediately remove them by local counterterms. So for instance, you can compute diagrams that arise from integrating out some fermion and get some anomalous contribution in the effective action to something like C cubed. But
let's see, how is C, scalar C defined here?
Let's see if we can. So C rho mu nu epsilon mu nu sigma is C sigma rho, and then the contraction of this G sigma rho gives you the scalar part of C. So because C has no non-trivial transformation under vial transformations, this would be completely equivalent to the following statement. I can write down...
Another question, how do you define C with a single index then?
You use... Oh, great. C mu is epsilon mu rho C. You choose the antisymmetric part of this contraction. Do this. So I can write down, for instance, QED with one fermion of charge Q. Let's say. This theory is, of course, anomalous, and there are two ways that one can remove this anomaly, one of which is completely stupid and one of which is the appropriate way to do things. So the anomaly goes as Q cubed, so I can add a second fermion of charge minus Q to completely cancel this anomaly. The other way is, of course, I can write down a local counterterm which decouples E and M from these fermions. So, of course, I can't do this because writing down a term like this breaks gauge invariance. But because these torsion tensors have no non-trivial gauge transformations, I can always write down these operators and completely screen any effects from the torsion, making this idea completely garbage. So that's two strikes. So Komargodski and Schwimmer in 3 dimensions doesn't work. So now I get to talk about the things that, given the manga and Steve Carlip are in the room, will cause me the most grief. Oh, right. So other people have tried to do what Komargodski and Schwimmer have done in 3 dimensions, and this is the notion of F-maximization. So they define a quantity F where they compactify a partition function on the 3-sphere, and they say that FUV is always strictly greater than FIR, and that rather than counting something by constructing some Wessmino action, computing this quantity F, if you compute it into theories that are connected by an RG flow, this statement should always be true. The problem is that F counts topological degrees of freedom, so that's one strike against it. The second issue is a bit more subtle. So if I consider Chern-Simons theory with n fermions, because this quantity F counts topological degrees of freedom, and they'll contribute as the log of the Chern level, if I pick sufficiently many light fermions, there's some scale at which the Chern-Simons, there's a topological mass for the Chern-Simons term. So once I renormalize below that scale, I don't have this log contribution. If I have sufficiently many fermions that are light, then I have a contradiction in terms of FUV being greater than FIR. And so this notion of F-maximization, they make it nice with all these computing the partition function and n equals 2 SUSY, but in some sense it's garbage. So.
But this work in 2 and 4 dimensions?
No, so they're using the basic notion from thermodynamics of this. Because there are no trace anomalies, there's no contribution to the internal energy in 3 dimensions. So they can, in some loose sense, define a number of degrees of freedom here. It's a and
I'm sorry, I didn't understand your statement. Something you have many light degrees of freedom, what makes it this value?
so if I have a Chern-Simons theory with n fermions, then if I count F in the UV, there'll be some contribution of heavy degrees of freedom. And so once I go beneath the mass scale for the Chern-Simons theory, I'll lose any contribution from here. But if I have a sufficiently large number of light fermions, then F in the IR is going to be larger than F in the UV.
Right, because the first one is negative.
Yes. Yeah, so it's monotonically decreasing above the topological mass of Chern-Simons theory, and beneath that, if you have sufficiently many light degrees of freedom, then you can violate this inequality. There's also
the number of fermions doesn't change,
Yeah.
right? So
if they're massive, I can integrate enough of them out. Yes.
I still don't understand that statement. Why, even if you don't have, why do you need a sufficient number? If you just have one, you can just, well, are you saying log k is negative?
At some point, it does become negative, but no, once I've integrated out these degrees of freedom, I can, well, so I can, yes, that's correct. There must be something I'm missing, but I know that this is the issue. Oh, there it is. So, the third way in which one can do this is using entanglement entropy. And so entanglement entropy will also count degrees of freedom. So how one defines...
Yeah, I don't know.
what was the answer?
I forget exactly how the proof goes. If you're terribly interested, I can tell you later. But I know that that's an issue with counting F.
So you just say the statement FUV bigger than FII is wrong.
Yeah, in the case of a
And why
Chern-Simons.
do people propose that?
The argument so far is that it's not sufficiently well understood how to write down F for gauge theories. So people have shown that if you take a free Maxwell theory and compute F, that you can get some arbitrarily large answer. So it's not believed that it's regularized well enough and not well understood. But it seems to make sense in a bunch of n equals 2 SUSY cases where it gives all kinds of nice answers. So perhaps not wrong, but not well understood in the case of gauge theories in 3 dimensions. So the approach we started now is using entanglement entropy. So how one defines entanglement entropy is you take a time slice sigma and you separate this in some way so that you have a subsystem A and subsystem B. So you take a pure quantum state defined by the path integral, and if you trace over the degrees of freedom inside A, because you start with a pure state, the entropy of what's inside will give you the entropy of what's outside. And so when I want to actually compute this entropy for a quantum field theory, it's not entirely obvious how one naturally computes this object. So people have used what's called the replica trick, where they take n copies of the field theory and analytically continue to non-integer n, and they just evaluate rho to the n. The picture that goes along with this construction is that when you introduce some entangling surface, you have to introduce a conical deficit around it. So let's say, for concreteness, that this is some Cauchy surface. If I have a copy of this sheet here, when I take an integral around one of these singular regions where I put this entangling surface, I have to identify the field points at this cut with this, so I'm integrating, let's see if I can do this properly, like this, and then I have to continue down here, this, and back up. And so, because I'm going around this point n times, I can identify this space with a conical space that has some conical defect that has, instead of periodicity that's 2 pi, it's 2 pi n. And so, people use this trick, but it doesn't have a nice physical picture in the sense that you're making all these replicas and analytically continuing when you could have arbitrary contributions to the entanglement entropy that don't make sense for non-integer n, but would in the case where you legitimately have n Riemann sheets.
Sorry, I should have asked earlier. Could you again what's this different surface and what's rho?
What is rho? Rho here is just a density matrix defined from the quantum. So,
Oh, okay.
yeah, so you place some quantum state on this, and you define the density matrix in the normal way, and then you take the trace over all the degrees of freedom in A,
Okay.
and you get the reduced density matrix of B, which is just the trace of A on the original density matrix you started with.
And those different surfaces because you have a branch cut.
Yeah, there's some singularity located at the entangling surface, and the way around it is to make copies.
Right.
So, 2 questions. One, the entanglement entropy is going to depend on what state you're in. So how is this going to tell you about something about the number of degrees of freedom in the theory rather than being just a statement about, at least partly a statement about the number of degrees of freedom in a particular state? You're looking at the vacuum only? Or?
Yeah, you're generically looking at things that are very close to the ground state.
Okay. And is this, do you have some demonstration, I'm not asking you to do it right now, but that this approach is going to give you the same count of degrees of freedom as the coefficient
Yes,
A?
I do actually.
Okay, good.
Yeah.
That's what I want to hear.
Yeah. So
Not
there's
necessarily
actually
right one.
a fairly simple, I wrote down the 2-dimensional example. I figured something like that would come up. So I can do this in 2 dimensions. All metrics in 2 dimensions are conformally flat. And so I can replicate the manifold in some very loose sense by changing the periodicity of theta and then appropriately rescaling R. And it's just normal. And so, based on how the Ritchie scalar transforms under conformal transformations, this will behave as, say, a box of log R in 2 dimensions will give me a delta function. So I'll get n minus 1 times something that's localized on the entangling surface. And so I use the VEV, I use the result in 2 dimensions. And then this tells me that I have to evaluate the conformally transformed Ritchie scalar on this class of metrics. And so this is how one replicates the manifold, and then when I use this definition of the entanglement entropy, I get the central charge C when I compute this.
Okay.
And so that was all the warm-up.
How does this relate to rho? I guess I don't see the transition. Yes. Could you maybe repeat the last sentence again? You said that I couldn't repeat it. Maybe I understand the second time around.
I was just using the fact that the trace of the stress energy tensor in 2 dimensions related to the Ritchie scalar. I'm saying that C is classifying all conformal field theories in 2 dimensions, and I'm just saying that if I take some conformal field theory that in principle can be defined, well, I'm taking some, so I'm taking some conformal field theory, I can write in a density matrix for it, and then I know that the density matrix will be related to the trace of the stress energy tensor, and so I use the result that in 2 dimensions, that statement is true, and evaluate the transformed R on some transformed set of metrics.
How is the stress tensor related to rho?
Yeah, that's what I'm listening. I just can't quite get it.
So it's easiest to see in the rotationally invariant case. So if I take some rotationally invariant entangling surface, omega, I want to talk about angular evolution. So rho in this case is just given by e to the minus 2 pi j. The VEV of j will be, well, h generates time evolution, h is related to t. This guy, and whenever this is some null vector defined on the surface, I appropriately define these guys in Higgs space, and I compute the VEV of j. In this case, the VEV of j is related to the VEV of t mu nu, which by that statement connects them.
I can't penetrate it, but I'm not really knowledgeable here, so continue.
Again, there must be some state, this must be in the vacuum state or something
Yeah.
like that.
Yeah, when one defines entanglement entropy, it's at the ground state or some close to ground state. So now, what we're actually working on is Marcus hates the replica trick with every fiber of his being. So he wants a physical picture for how to compute the entanglement entropy without relying on this replica trick. And so when you're using the replica trick, you're identifying implicitly when you're doing these integrals, I conveniently deleted that picture, the two parts of these fields when you're going around this entangling surface have to be identified. So if one writes this down in a path integral, then there's some constraint placed on the set of field configurations you're using. And so Marcus had the idea that this is equivalent, well, that this is equivalent to just placing an orbifold, meaning I take this interval, identify these 2 points, and I write down only field configurations for which this is true. And so away from the orbifold, I won't see anything peculiar. Close to the boundary, I'll see all kinds of singularities and things like that. And so rather than working on an n-sheeted copy of this space,
Why does it have to be an orbifold?
we're choosing it to be an orbifold because it works out.
But before it was, they just had to agree on the time slice.
No, before they had to agree on some arbitrary analytic continuation in n to be able to define what their entanglement entropy was. They're placing a series of sheets, and then they're replacing the space with some conical deficit space.
The delta function is not equivalent to an orbifold.
Why is that?
It's just constraining them to match
Mm.
on some surface. But the orbifold is saying that arbitrarily far away from that surface, they're related.
Mm-hmm. Right. I mean,
One's local and one's non-local.
I agree. But that's only really visible near the boundary, isn't it? I mean, if you're looking into a mirror and you excite something, you'll see an excitation. There has to be some energy that's gotten out of that by making that excitation. But if you're sufficiently far away, you make a particle, and that's all you need. You have no knowledge of what's infinitely far away.
I mean, I'm moving along through time,
Mm.
and if I go through an orbifold in time, then the rest of my life is the reflection of the first part of my life.
Mhm.
But if I have a delta function, that just tells me I move along, and the rest of my life is continuous with my previous life. It's very different.
Mm. Don't necessarily, but so
If you could show that, if you could really show that in your computation that all of the important contributions come from right at the boundary, then it wouldn't matter.
and that's generically true. And there's all the bad divergence are localized on the entanglement surface.
Okay, so you're just looking at the divergent parts?
Yeah. The divergent parts are the ones that contain the information about local degrees of freedom, or about degrees of freedom in your field theory.
Okay.
So why are you using orbifold language at all?
Because Marcus hates the so the analytic continuation is not in principle well defined. There are some, like when you do dimensional regularization, there are a set of axioms and they tell you that this is the way one should analytically continue to non-integer dimensions, and so you have a way of evaluating these things. There's no real guiding principle in terms of how one says, I'm taking n copies of this sheet, suddenly n is not an integer, and I can take well-defined derivatives of these things. And so the basic idea is that if you regulate the space in some way, and you're really talking about the appropriate identifications that you have to do when you're constructing these sheets, then you can evaluate all of these quantities on just some geometry that we constructed from first principles, and you don't have to arbitrarily make n copies and place cuts everywhere and put cones and whatnot. So the solution to this is to, because all the singularities are localized on this entangling surface, is to blow up the entangling surface so that it has some UV cutoff L inverse, and work now on a regulated space that has some reflection symmetry. And it turns out that this regulated space is something akin to a wormhole in the sense that if you follow the radial coordinates, there's some minimal length L, and R goes to positive infinity, negative infinity. And it turns out that if you take this background geometry and put some field in there, you get the appropriate count of degrees of freedom, along with divergences that are associated with the size of this blow-up, shrink to infinity. So you get the right count of local degrees of freedom. And so what we're working on now is we've shown that you get the area law back in terms of the appropriate entropy would work on this background space. And now we're working on understanding how gauge fields look in this setting and see if one can appropriately compute degrees of freedom in this background setting rather than this end-sheeted bit of nonsense. And so that's what we're doing. Questions?
Okay, let me ask you one more question. This is a more conceptual issue, I guess, but I'm a little, I guess I'm confused about the way you are describing the problem that you're addressing. I understand what the question is, but when you describe this as counting numbers, the number of degrees of freedom, I don't quite understand what that means. I mean, for instance, in 2 dimensions, it's true that if you have n free bosons, that the central charge is just n. But it's also true that if you have a single self-interacting boson, you can put in a self-interaction that makes the central charge arbitrary, essentially. So in what sense is this, do you have some deeper understanding of why this is really number of degrees of freedom, or is this just a sort of abbreviation for the coefficient of the anomaly?
I would say, best we can say what the coefficient is of the leading, in this case, linear divergences from the 3D action that will appear in the entanglement entropy.
Okay.
But yeah, there should be some, I mean, spiritually it's the same thing as F in some sense. So unless something works out in the cases where F is failing, I agree, it's only going to give you that coefficient, not necessarily some count of the degrees of freedom in some proper sense.
I mean, I'm asking because this is something that I've been puzzled about in 2 dimensions for many years. The fact
When
that,
you say it's arbitrary, it's really arbitrary or in some range?
oh, take Liouville theory, and the central charge is just the coupling to the scalar curvature. And you can make it anything. There is some different object called the effective central charge that involves the central charge and the lowest eigenvalue of and the lowest weight state, which is something more like a count of degrees of freedom, but I can make that look really strange by choosing strange enough conformal field theory as well. It's really frustrating because I would like to have some more physical understanding of the central charge, but I can find lots of counterexamples to anything that I can come up with.
Any other questions? Kevin? Okay, if no, thanks Kevin again.